Good morning, welcome to new lecture. Today I will continue to review examples. Let's look at this frame. Problem statement. We have this frame. And we want to draw moment diagram and shear diagram for this frame. This frame A, B, C, D. The only external load we have, it is concentrated moment at joint B. And you see joint B and joint C, they are rigid joint here. So in order to draw moment diagram and shear diagram, first step I should find reaction. dy I can find, it is very easy to find dy. If I take moment respect to point A is hinge, I can find dy. What is the dy? dy times L minus M is equal to 0. So from here, dy will be M over L. If I write summation of force in horizontal direction, Ax will be 0. If I write summation of forces in vertical direction, Ay plus dy is equal to 0 because there is no external load in vertical direction. From here, Ay will be negative M over L or M over L in opposite direction. So let's look at the shear diagram and moment diagram. There is no any force perpendicular to the AB column, so shear force here will be 0. This ML will transfer through AB column to this BC beam, so it will create shear. I will move down from B M over L down. There is no other force. I will continue, and this M over L will transfer through the column BC to here. So I will move M over L up, I will close the diagram. Again, there is no other force perpendicular to DC. DC column shear force is equal to 0. About moment diagram, again, I will put dashed line inside of the frame. So let's look at the joint A. Joint A is hinged, there is no moment here, so it is 0. If I move from A to B, just before B, if I cut it, there is no force perpendicular to this member. So force perpendicular to that member will create moment. So no moment 0. At joint B, we apply moment M. So we have M. And that moment M, if I rotate joint B at M direction, it will create tension in the BC part in dashed line, so it is positive moment. At joint D, note D here, it is hinge, moment is 0. There is no force perpendicular to the DC, entire column is 0, so from M it comes to the 0. It will be one triangle like this, positive M. If I move clockwise inside of the frame, you see in the direction of movement, moment magnitude is decreasing. That means shear should be negative. Derivative of moment will give us shear force. Derivative of diagonal line will be straight line. So that is right. Let's look at the next one. Next example we have here. P, P, A, B, C, D. I want to draw moment diagram and shear diagram for this beam. Let's see what is happening here. If we look at today, the formation of this beam, if we know the concept, it is clear. This BC part, it is unstable part. BC part will not transfer any load from left to right or from right to left. So we have here another load P. Both are P and P, and the length is, for each part is L. And I can prove that. How I can prove that? If I cut this part and I look at the free body diagram for that part, what I have? I have BC segment. Here assume I have BY, I have BX, I have CY, I have CX. If I take moment respect to point B, Cy times L is equal to 0. If I take moment respect to point B, Cy times L is equal to 0. From there, Cy is equal to 0. If I write summation of forces in vertical direction, By plus Cy is equal to 0 because there is no external load in BC part. So By is equal to 0. So you see, Cy is equal to 0, By is equal to 0. So the contribution of BC from this load, it is 0. It will not have any contribution. So this P will transfer here. This P will transfer here. So if you look at the one part only, it is like this. This is P, this is P, A, B. This is cantilever beam. And moment diagram for this, we know that it is negative PL. BC part, it is 0. Again, CD part, it will be negative PL. This will be moment diagram. Shear diagram will be P up. There is no force. P down. 0. Again. P down. There is no force. P up. Negative. This will be our shear diagram. So moment diagram, shear diagram. Next example. Next example is one cantilever beam subjected to triangle load. So we have this beam. Okay, we want to draw moment diagram, shear diagram for this beam. First, let's find reaction. What is here? It's point A, point B. What is AY? Summation of forces in vertical direction is equal to 0. AY minus entire load downward. It will be area underneath of that triangle will be W times L over 2 is equal to 0. From there, AY will be W L over 2. Moment at support. If I take moment respect to point A, it will be resultant force means WL over 2 entire load times the distance of resultant up to point A. The distance of resultant, it will be in the centroid of that triangle, and centroid of the triangle from the point A, the distance will be 2 over 3 times L. So times 2 over 3 times L, the moment will be W L squared over 3. Now, shear diagram. As much as reaction, I will move up, WL over 2. Derivative of shear, it will give us the intensity of the external load. From A to B, the intensity of the load is increasing. So the shear from A to B, if I look at the shear diagram, derivative of shear diagram means the slope of diagram. Shear comes from WL over 2 to the 0. But the slope means derivative, it will increase because from A to B the intensity of load is increasing. So this will be shear diagram. This is diagonal line, 1 degree higher order. If this is linear, that will be second order or parabolic, so this will be square shape. And the slope of this curve, you see from A to B, slope is increasing. Here slope is this much, here slope is this much. From A to B is increasing because the derivative of this curve means the slope, it will increase because from A to B, the intensity of load is increasing. Moment at point A, we found it. It is WL squared over 3. Moment at point B, it is 0. Why it is 0? Because it is free end. In free end, always moment is equal to 0. But derivative of moment is shear. From A to B, magnitude of shear is decreasing. So the slope of this curve should decrease. The slope is decreasing means this kind of curve. You see slope here, bigger slope, here is smaller. Derivative of one curve means slope of that curve. Derivative of moment is shear. Derivative of shear is intensity of external load. I proved that before in structural analysis and in statics course as well. So this will be shear diagram. This will be moment diagram. Moment will be negative because we have compression underneath of the beam. Compression underneath of the beam means negative moment. Shear will be positive. Okay, let's look at 2 degree of indeterminacy for different structure. You see it is pure hinge, all members come to the hinge. This here it is continuous and hinge comes to this member. You see the difference. A, B, C, D, E, F, G, H, I, J, for example. I want to see how many degrees this structure is indeterminate. So, if you remember, I proved this formula in class. Degree of indeterminacy is equal 3 times member plus reactions minus 3 times number of node plus condition equation. Here number of members in this problem, it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Number of reactions, 3 fixed support, each one 3 reaction, 3 times 3 will be 9. Number of nodes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 nodes. C, condition equation. If the number of m members reach to one hinge, the number of condition equation C will be m minus 1. Here 3 members, so C for this will be 2, C for this will be 2. Here, because this is continuous, we will consider that as a one member. This is another C, here is 1. So entire C, 2 plus 2, 4 plus 1 will be 5. If we plug here now in the formula, it will be 33 plus 9 minus 30 plus 5. This will be 42 minus 35, this will be 7. So the number of unknowns more than equation. How many unknowns we have more than number of equilibrium equations? 7 unknowns. Okay, let's look at the next one. Next one is this shape. A, B, C, D, E, F, G. Okay. Let's look at the number of members. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Number of reactions. 3 here, 1 here, it will be 3. Sorry, 2 here, 1 here, it will be 3. 2 reactions, 1 reaction, 3. Number of nodes. 1, 2, 3, 4, 5, 6, 7. And 7. C. Okay. 3 members reach to the hinge. 2 here, 2 here, 2 here, 2 here, 2 here. Here, 1, 2, 3, 4, 5, 6 members, so 5 here. So 6 times 2 will be 12 plus 5, it will be 17. So degree of indeterminacy of the structure will be 36 plus 3 minus 21 plus 17. That will be equal to 39 minus 38. So it is 1 degree indeterminate. Next example. For this structure, again, M is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So number of members, 12. Number of reactions, 2 here, 2 here, 4, 3 here, 7, 2 here. 7 plus 2, it will be 9. And number of nodes, 1, 2, 3, 4, 5, 6, 7, 8, 9. C. 3, 3, 3, 3. 4 times 3 plus, here all we weld these members together. This member only we attach using hinge to these 3 members. So here is 1. So C will be 4 times 3, 12 plus 1, it will be 13. So here 36 plus 9 minus 27 plus 13. This will be 45 minus 40, it will be 5. Next one. This is our structure. So A, B, C, D, E, F, G, H, I. Number of members: 1, 2, 3, 4, 5, 6, 7, 8, 9. Number of reactions: 3 here, 3 here, 6, 2 here. It will be 6 plus 2, 8. Number of nodes: 1, 2, 3, 4, 5, 6, 7, 8, 9. N is equal to 9. C, 1 here. This is, you see, these two members are continuous. This hinge comes here, 1 here. Here we have 2 because you see, this is not hinge, it is internal roller. It releases the axial force and moment. So 2 internal forces are 0 here. One of them is axial force, it is free to move in axial direction. Another free to rotate, internal moment. So C here is 2. So C, 1, 1, 2, it will be 4. From here, we can write 27 plus 8, 3 times m plus r, minus 3 times n, 3 times m, 27 plus r, 8, minus n, 3 times 9, 27, n was 1, 2, 3, 4, 5, 6, 7, 8, 9. So 27 plus 4c. Formula 3n plus r minus 3n plus c. From here, this will be 35. This will be 31. It will be 4. Okay. Next example. Here we have one frame like this. This is rigid joint. And we have here one pin support. This is L. This is L. A, B, C, D. External load is triangle distributed load. This is W. We want to find, let's see, A, B, C, D. We want to find MC, moment at joint C. And you see, this is rigid joint. First member DC and BC we attach together using weld. We weld together, it is rigid joint. Then we using pin support we attach to the ground. So there is a moment here. Moment here is 0, this is 0, this is 0. Let's see what is happening. AB part, what is happening? AB part is under this load. What is the external load? It is one triangle load. What is entire load? Area underneath of that triangle. Area underneath of that triangle will be W times L over 2. So entire load downward, it is W times L over 2, area underneath of this triangle. From this entire load, half will transfer here, half will transfer here. This half is transferring here, it will be WL over 4, half of this F. That will move because this support is free to move in vertical direction, so no resistance against this load. This load directly will transfer to the column AD. From there it will transfer to the node D. So this load through this column will transfer here WL over 4. That load times the distance up to point C, it will create moment that will be equal to WL over 4 times L. That will be equal to WL squared over 4. This load, it is in axial direction, it moves, it comes here, but because it passed through C will not create moment here. So the moment at joint C will be WL squared over 4. If you understand the concept, if you visualize this kind of problem, you don't need to solve it. Of course, you can solve it, cut part to different parts, draw the free body diagram, find the reaction, apply those reaction in inverse direction as action load. That will take a long time, but if you understand the concept, you don't need solution for this kind of problem. These members, they will communicate to you. They will tell to you what is happening, and this joint will tell you internal moment here is equal to WL squared over 4. Please pay attention to the concept. Try to understand the concept. So, try to develop that skill. You can communicate with the structure. If you are able to communicate with the structure, you will recognize what is wrong, where is your mistake, and in most cases, even you don't need solution. Answer is over there. Next one. We have this structure. L over 2 L. We apply load P here in the distance of X. So A, B, C, D. Problem statement says find X so that the deflection at point B, vertical deflection at point B is equal to 0. So we know the vertical deflection at point B is equal to 0. Now what is X, where I should apply P in order to have vertical deflection at point B is equal to 0. This is the problem. Very simple problem. Let's see, if you cut here, what is happening? You have this cantilever beam AB. This part will apply one load here, another moment here. Why? Because if you apply this P in the X distance, and this is L, and this is L over 2, okay? What are reactions here? In order to have this piece in equilibrium, this is P downward, you need one P upward. P times this distance, which is L minus X, it wants to rotate this piece counterclockwise. So you need moment M is equal to P times L minus X in inverse direction in order to keep this piece in equilibrium, cancel that rotation. These are reaction load. The action of this part to this beam, it will be the force and moment in inverse direction. So this piece will cause, we will have one vertical load here, P, another moment counterclockwise, M is equal to P times L minus X. So we can now simplify that problem to this problem. Now we know delta B is equal to 0. What caused delta B here? Let's look at to the superposition. Make problem easier. We have cantilever beam subjected to concentrated load at point B, free end, plus we have cantilever beam subjected to moment M is equal P times L minus X counterclockwise. Deflection we will have here, we will have two deflection. One of them, point B, will move down like delta B1 because of this load. Another point B will move up delta B2 because of this moment. If these two deformation, the magnitude of these deformation, they are equal, in that case delta B will be equal to 0. Why? Because one of them downward, another one is upward, magnitude are equal, so they will cancel each other. And you see, from superposition, I can divide this system to these systems. The load I'm applying here, then I'm applying the moment. If I add these together, I will get initial structure. So, if I apply load only in cantilever beam, several times I calculate this. What is the deflection? Will be P L cube over 3EI. You can find from different methods, but we know if we have cantilever beam subjected to concentrated load at free end, the deflection will be PL cube over 3EI. Using virtual work method, in 1 minute you can prove this. If you have cantilever beam subjected to the moment, the deflection will be M moment L square over 2EI. Using virtual work method, I proved it before. You can prove it using conjugate beam method, moment area method, or virtual work method. You can find if we have cantilever beam subjected to moment M, what is the deflection? It will be ML square over 2EI. These two deflection, they should be equal. So P L cube over 3EI should be equal to M. Instead of M, you can put magnitude P times L minus X times L squared over 2EI. EI and EI from both sides, they will cancel. From here, if you find X, you will find X is equal to L over 3. So, make a story short, if I apply this load downward at X is equal to L over 3, this deflection at point B will be equal to 0. Try to use superposition. In most cases, superposition will help us. It will make problem very easy to understand, to digest. So, as a beginner, try to use superposition. Later on, maybe without superposition, you can do it. But if you want to solve as a beginner, it is good you use superposition, practice, that will create sense in your brain. So use superposition. This one, A, B, L, L, P, A, B, C, D, E. We have this structure. These are L and L. EI is constant for entire structure. We want to find deflection at point B. What is the deflection at point B? In vertical direction, delta B. And the only load we have here is this P. So, in order to find, we can cut from here look at to this side to see this side, what is happening and what is the action of this side, right side, on the left side. Because for any action there is reaction, equal and in inverse direction. So if I cut this and I apply here dx and dy, this is L, 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 you apply P here. Summation of forces in vertical direction is equal to 0. From there you can understand dy is equal to 0. Summation of moment respect to here should be equal to 0. Why? Because top side will create moment clockwise, bottom side will create moment counterclockwise. They should balance each other. They should cancel out each other effect. This part, it is like seesaw system. It should not rotate. In order to satisfy equilibrium, okay, Bx times L should be equal to P times L. From here, Bx will be equal to P. Bxp, this is P, this reaction will be 2P. So now, let's come back to real structure. Here, the reaction is 2P. This part applies axial force in AB direction, P, and vertical load, it applies to AB part, it is 0. So if I cancel this part, if I remove this part, the action of this part on the AB part, it will be one axial force and one vertical load. Vertical load magnitude is 0. So that will not create any deflection. Axial load can create deformation in the AB part, but because in this problem we neglect the axial deformation and this load perpendicular to the AB is equal to 0, so delta B in vertical direction will be equal to 0. Next one. We have this frame A, B, here we have load 2P, here we have load P, this distance is 2L, this is L, from here to here it is 4L. We have this frame, you see the dimension, EI for entire frame is constant. We want to find the distance from A to B after deformation. So distance from A to B after deformation. Look at to the top part. What we have in top part. If point A, we apply this load, it moves from left to right. Point B, if we apply this load, it will move from right to left. So both of them, they are able to move in horizontal direction. Top part, if I remove top part is something like this. If I apply load here and here, there is no stiffness against those loads, or there is no any bearing capacity. That part is unstable part. it is clear if I add this load, this easily will rotate like this. And this part, top part, will not show any resistance against those loads. So this part, it is useless part here. Now, what we have here, we will have two cantilever beam, one of them AC, another BD. If we apply load on the cantilever beam, this deflection, I can calculate it delta A. That will be equal to the load, which is 2P, the magnitude of the load, times length cube 2L cube over 3I. BD part will bend like this and point B will move from right to left. Delta B will be load P, length of the beam, it is 2L cube over 3EI. So initially the distance from A to B was 4L. Now the distance will be 4L minus delta A plus delta B. That will be equal to 4L minus, that will be 16 PL cube over 3EI. Okay, and this will be P8 PL cube over 3EI. So distance AB will be equal to 4L minus the summation of this, which is 24 PL cube over 3EI. That will be equal to 4L minus 8 PL cube over EI. You see, it is very simple problem. It is very simple problem. It seems scary a little bit in the beginning, but if you pay attention to the concept, visualize it to see how it will deform, you see it is very easy problem. You don't need any solution. Let's look at to the next one. A, C, this part is rigid. Rigid means EI goes to infinity. No deformation in this part, or the cross section is very big. Roller B, we apply concentrated moment M. This is L. From here to here it is 2L, for example. Of course I didn't draw using this scale. It seems equal, but problem statement, AC part it is 2L, BC part it is L, and EI for this part is constant, for this part it is infinity, so it means rigid. Problem statement says find slope at point B. How this system will deform? If I apply moment, this BC part will rotate like this, and AC part will bend like this. Here, if I find deflection at point C, theta B will be equal to, in this triangle, because we are in small deformation range, so theta B, this angle, will be delta C divided by L. Tangent of this triangle in small deformation is equal delta C divided by L. So if I find delta C, that's it. I know the answer. What is delta C? This rigid part, C, B part. I'm applying moment here, M. This moment will cause force here. How much is that force? I can cut here, I can find Cy. What is the Cy? You see, M, if I take moment, for example, respect to this point B, if I take moment respect to point B, I will have M counterclockwise positive minus Cy times L is equal to 0. So this M will create here reaction of M over L. If I take the other side, M will be equal to Cyl. From here, Cy will be equal to M over L. This M creates reaction at point C, M over L. Or in another word, this M will create action force here equal to M over L. That force will cause deflection. What's the deflection? In cantilever beam, if we apply concentrated load, you can find using several methods, but as I mentioned, as I said several times, memorize those simple cases. It will be load M over L, like P times length of AC cube 2L cube over 3EI. From here, the formula is PL cube over 3EI. Here P is M over L and our L is 2L. So, from here, this will be equal to 8mL squared over 3EI. I have delta C, I will plug here. Theta B will be equal to 8mL over 3EI. Next problem. If I find problem statement, okay, nice. A, B, C here is subjected to uniform distributed load. Intensity of load, it is 20 kips per feet, 2 feet, 5.5 feet. Problem statement says find reaction at point B. What is reaction at point B? Again, it is very simple problem. We can use superposition. First, I can remove this part and apply the effect of that part. That part for AB segment will apply one load and one moment. That load will be resultant load for this system. It will be 20 times 2. It will be 40 kips. Moment will be resultant moment for this. It will be 20 times 2 times 1. That will be 40 kips feet. Now I want to find reaction here. How I can find? Using superposition, I can divide this to these three systems. One AB subjected to only load 40 kips, plus another this beam subjected to only moment 40 kips feet. Another this beam subjected to reaction at point B. What is happening? Because of this load, point B, because of this load, point B will move down and we will have deflected shape, something like this. This deflection I call it delta B1. This cantilever beam, because of this M, again it will deform. How much? It is delta B2. Because of this reaction force, it will it will deflect again, and the deformation will go up this time. It will be delta B3. Why? Because this reaction is upward, this is downward. So downward load will create deflection in downward direction. This moment here, it is clear, it will create deflection downward. Reaction will create deflection upward. What is this delta B1? Delta B1 will be load 40 times the length of that span 5.5 cube over 3 EI. Because of the formula, it is for load P L cube over 3 EI for cantilever beam deflection. For concentrated moment, it is M L squared over 2 EI. If you cannot remember, you can prove it. Easy. It is easy to prove using virtual work method, conjugate beam method, or moment area method, or any other method. You can prove in 1 second. So, delta B2 will be M 40 times L squared, L here 5.5 squared over 2 EI. Here R, it is again load, so delta B3, it will be load which is RB, reaction at B, L cube 5.5 cube over 3 EI. In reality, if come back to the real structure, what is the formation here? It is 0. Point B will not move down or up because we attach to the support. It means delta B1 plus delta B2 should be equal to delta B3. So delta B3 should be equal to delta B1 plus delta B2. And you see, if I add all these three beams, I will get initial beam. So from here, R B 5.5 cube over 3 EI should be equal to 40 5.5 squared over 2 EI plus 40 5.5 cube over 3 EI. You have one equation, one unknown. EI from both sides, they will cancel. It will cancel out and you can find RB here. This is RB. 5.5 cube is equal to 45.5 squared. This is again cube. So one equation, one unknown. You can find reaction at point B. Okay. Thank you so much for watching this lecture. See you next session. Bye bye.